Hello, so welcome to this presentation on REL61. REL61 is AIM Solder's cost-effective SAC305 alternative with enhanced performance. First, I just want to describe the AIM solder difference. So it's worth noting that AIM has been around for more than 85 years. We are a global company with local support and product offerings. We really pride ourselves on our responsive support. We are also innovative and we have a robust R&D program. We aim to provide consistent quality worldwide, applying the same quality standards at all of our sites. And we also offer sustainable solutions. So first, let's have a little overview of REL61. So REL61 is a solder alloy, and it is a lead-free solder alloy. And the thing to note about lead-free alloys is they come in different generations. The first generation was SAC305. SAC305 is a tin, silver, copper alloy. It was is compatible with existing processes and lead components. Some disadvantages of this alloy is that compared to traditional tin lead, it was higher in cost. It does have some copper dissolution issues, can have some poor mechanical properties. Sometimes tin whisker growth is an issue with this alloy, and it has poor aging performance. To improve outcomes, second generation alloys were developed. So in this category are variations of SAC, that tin, silver, copper alloy with different percentages of silver and copper, and also SN100C. So these alloys were often lower in silver content in order to lower the cost. Still compatible with tin lead. SN100C reduced some defects and improved joint strength. But many of these alloys still have poor mechanical properties and also higher melting temperatures. There are third generation lead-free alloys, and there are many alloys in this category. Our REL61 alloy fits within this category. It is a low silver alloy, but it also has bismuth added, so it is lower cost. The addition of the bismuth actually lowers the melting point a little bit. It has improved strength and performance, seems to mitigate tin whisker formation, and has very good aging performance. The one major drawback of this alloy, however, is due to its bismuth content. It's not compatible with any processes that still have lead in them. Oops, oh, next slide, sorry about that. So our REL61 alloy is, it's notable for several reasons. We mentioned that it is one alloy that does it all. It's available in bar form for wave soldering. It can also be used in selective soldering, and it comes in paste for SMT applications. It's also available in wire. It's a low-cost SAC305 alternative, enhanced reliability versus many of those other low or no silver alloys, really good wetting properties, reduces voiding. It has a higher strength and hardness compared to many SAC alloys, very good barrel fill when it comes to wave and selective soldering. Low solder pot maintenance is required. It mitigates tin whisker formation, and it has a slightly lower melting point than many of those other alloys. This is just a brief overview of some of the physical and mechanical properties of REL61 compared to SAC305. Again, you can see the slightly lower melting temperature, very similar density and wetting time, but it has a higher hardness. Thermal conductivity isn't significantly different. Many of the other properties are somewhat similar, slightly lower conductivity, but much improved tensile strength after aging. One of the big selling factors of this alloy is its lower cost. So this particular graph shows a savings range of 10 to 20%. We've actually had, so price varies depending upon metals prices in the market. but sometimes these savings can be as much as 40% even when switching from SAC305. So REL61 has better performance in general across many applications. So really good print transfer efficiency, improved wetting. Another thing is it does not degrade with thermal aging. So the images we see here, we have SAC305 and REL61 microstructures when they are first cast. And then after thermal aging, we see that SAC305 develops these structures within it, and those are avenues for cracking and joint failure. REL61, in contrast, does not experience that same change. REL61 is really great for wave and selective soldering applications. Oftentimes, people ask about phosphorus content. Some alloys have phosphorus added in for wave soldering to reduce dross, but REL61 does not. We do not add phosphorus to our REL61. REL61 actually naturally drosses less due to its composition. So phosphorus in selective soldering applications can degrade nozzles. Since REL61 does not contain phosphorus, this is not an issue. REL61 also shows superior barrel fill performance in both wave and selective soldering applications. Many people ask about REL61's compatibility with other alloys and processes. So REL61 is composed of a low silver SAC alloy, so tin, silver, copper, combined with small amounts of bismuth and grain structure refiners. REL61 is compatible with most elements in lead-free environments. So this includes SAC alloys, nickel finishes, trace germanium. You can use REL61 in combination with SAC BGAs, for example, and that's not an issue. However, due to REL61's bismuth content, it is not compatible with alloys and components that contain lead. And that's because bismuth can combine with lead to create sort of a really low melting eutectic that can cause joint failures. But as long as your process is lead-free, REL61 performs very well. We have a whole host of internal and third-party test results which demonstrate REL61's robust performance. This is just a very brief overview of some of those results. So if we look at intermetallic growth, REL61 reduces the growth of the IMC layers, which improves solder joint durability under thermal stress. Here we see it compared with SAC305, a tin copper nickel alloy. And we see that REL61 has the smallest intermetallic layer of the three. REL61 also wets very well. This is a wetting comparison where we measure the contact angle of a molten drop. The smaller the angle indicates better wetting, and REL61 had the smallest of the angles measured. This is another wetting comparison where we look at wetting force over time. And in this particular test, we see that REL61 is comparable to SAC305 on this test. This is a test where we looked at tensile creep for when we aged the solders for 24 hours at 150 Celsius. We see that SAC305 experienced quite a bit of increase in creep strain, whereas REL61 did not. So the creep performance of REL61 was shown to be superior to SAC305 in this test. This is one of our favorite tests, shows the difference in tensile strength, and we are comparing that strength when the alloys are first cast versus when after they have been aged for 24 hours at 150 Celsius. What we notice is that as cast, REL61 and SAC305 have the same tensile strength, and both are stronger than the other alloys tested. However, after aging, REL61 maintains its tensile strength, only dropping very slightly compared to all of the other alloys, including SAC305, which lost about half of its strength. If we compare hardness, REL61 has a hardness that's about twice that of SAC305 and a tin copper nickel alloy. We've also looked at thermal cycle test results with this alloy. So here we are comparing REL61 with SAC305, treating SAC305's performance as the baseline and looking at the results across different components. We see with the 3 different components tested that REL61 performs either equal to or better than SAC305. This is a thermal shock test, so we change the temperatures more rapidly and see how these alloys perform. At 50% test completion, there were no failures with REL61, whereas 40% of the resistors assembled with SAC305 had failed by this point. In the final result, 60% of REL61 joints survived, while only 20% of SAC305 joints did. REL61 essentially doubled the lifetime of an assembly compared to SAC305 under thermal shock conditions. These are additional thermal shock tests on different components. And again, we see those same types of results. REL61 significantly improves the lifetime of the assembly. We've also done vibration tests, and here we see REL61 and SAC305 having comparable performance, although REL61 experienced a slightly lower failure rate at the beginning of the test compared to SAC305. We've also done drop shock tests. This particular test compared REL61 with REL22 and SAC305. It should be noted that REL22 is our high reliability alloy, and it will generally perform better than REL61, but it's also a bit pricier than REL61. It is a high performance alloy. But what we do see is that REL61 does outperform SAC305 and shows less variability than the SAC305 in this test. Some people are concerned about tin whisker growth, the growth of these little tin whiskers off the surface. And we performed a tin whisker test under conditions of 85% humidity at 60 Celsius for 3,100 hours. And what we see is that SAC305 shows tin whisker growth under these conditions, whereas REL61 does not. So REL61 appears to mitigate tin whisker formation. We've also looked at voiding, which is a common concern. Here we have SAC305 compared to our M8 REL61 paste, and we see significantly less voiding in the REL61. Print performance is also another concern, so you really want your paste to be able to remove from your stencil smoothly, and we have had very good transfer efficiencies with our REL61 pastes. Another thing we look at is what does the alloy look like after it is melted? So something to note, SAC305 often has a sort of non-uniform appearance with some shiny spots and some dull spots, whereas REL61 has a relatively uniform matte appearance. And the significance of this is with usually with inspection. So when you do automated optical inspection, that equipment is basically shining lights on your solder joints and measuring what is reflected off of them. So if you have a non-uniform surface like with SAC305, you can get much higher error rates in those tests. REL61 does not have that issue. And so a lot of people like it because it reduces the error rates and hence the time spent rechecking things in production. This is just another example of how these alloys look after reflow. And again, we see that uniform finish on the REL61 compared to the non-uniformity of SAC305. We actually performed a test where we looked at the AOI results of these two alloys. And we can see on the left, the REL61, the differences in colors are sort of indicating how much variation there is on the surface. And we see much less variation with the REL61 compared to SAC305. Here's another image showing the same thing. We get much more uniform appearing results to those cameras, which again can reduce error rates compared to the SAC305. And this is just another image showing that same thing again. Through-hole reliability is another area where REL61 shines, and we just see some images of these joints showing that REL61 creates very nice joints in through-hole applications. This was a test that was performed. These are the results of the test here on this slide. And we see after some thermal cycling, SNCU07 was showing some failures at 750 cycles, as was SN100C. We show SAC305 showing failures at 1500 cycles, but REL61 maintaining its performance through 2000 cycles. REL61 has very good barrel fill in wave soldering. So it tends to have better barrel fill and solder flow versus many other low and no silver alloys. If you need to switch your solder pot from a SAC alloy or a tin copper nickel alloy to REL61, it's worth noting that no pot wash is required as long as you are switching from a lead-free alloy. These are the dross test results. So the important thing to note about dross is that it's highly dependent on your application and your setup. So we perform a laboratory test where we test these alloys under identical conditions and measure how much dross is formed. So the relative amount of dross formed by REL61 was significantly lower than the other low no silver alloys, as well as SAC305. We also see that REL22 performed even better. And again, REL22 is our high reliability alloy. It's sort of in a different category. REL61 we see as if you need to replace your SAC305 with something that's more cost effective without compromising on performance, then REL61 is the alternative for that. Next, we'll look at some direct comparisons of REL61 with SAC305 and some common low no silver alloys. Compared to SAC305, if we look at metrics such as cost, hardness, thermal cycling performance, IMC growth, wetting, tensile strength, as cast and after aging, the luster, which again affects the AOI performance, thermal shock, vibration, hole fill, and dross, we see that REL61 outperforms SAC305 in almost every single one of these metrics. When we compare REL61 to SN100C, we're again seeing either comparable or superior performance in REL61. SAC307 is a common low silver alloy people choose to save costs compared to SAC305. And we see REL61 significantly outperforms it across nearly every metric. Next, I want to go over some success stories, so some situations in which customers have used REL61. So in this case, we have our M8 REL61 paste enabled cost reduction and resolved flux residue issues. A manufacturer had wanted to consolidate their solder paste supply with AIM. So to make the case to one of their customers who was using a competitor's SAC305, they investigated the use of M8 REL61 for the same application. So this same customer also had some reported issues with the incumbent paste due to excessive flux residue on pads and test points, which was causing some problems. The solution was to try out AIM's M8 REL61. The end results were positive. There were no issues observed, even with using the incumbent reflow profile. Post-reflow solder joints met IPC acceptance criteria for Class 2 products, and flux residue was minimal, and AOI inspection found no defects. So it showed better wetting, printing, and residue compared to the competitor's SAC305. Again, this is just a summary of the products and services used in this application and the success metrics. They were able to save costs, consolidate with a single supplier, reduce residue, improved wetting, and printing performance. As another example, M8 REL61 paste performed well on a new project with complex high thermal mass boards. So a manufacturer that had previous positive experience with this paste wanted to see if they could use it for a new product line. They tried out M8 REL61 on the assembly, and it required an extended profile because of the high thermal mass and the high complexity of this build. So the end result was very good solder joints, minimal residue, and minimal voiding, and they approved the paste for development. So they were able to save costs, they experienced minimal voiding, and they had good performance on what were complex boards. As another example, M8 REL61 outperformed a competitor's SAC305 paste. It reduced voiding and eliminated solder balling. So they were making an effort to migrate from SAC305 to REL61 as a cost savings project. They wanted to evaluate the performance in a complex project in which the incumbent paste had some issues. And these issues included, again, solder balls on the ground plane of a QFP component. They tried out REL61, and they had very good results with their voiding. The end result was they were able to save costs. They reduced their BTC voiding from 23% down to 16%, BGAs from 12% down to 5%. The solder balling issue was eliminating, and the residues were clearer in appearance. As another example, we had a customer trying M8 REL61. They were having problems getting a clean squeegee wipe using the competitor's SAC305 paste. They were also experiencing dry joints, which were causing failures of the end product. Another thing that was happening is they had a lot of automated optical inspection false passes, which was an issue. So they tried out our paste. And just to summarize, they experienced improved wetting results, improved printing results. Their AOI false readings were reduced. And again, that's due to the luster of REL61, which has that uniform finish. And they also had clearer residues. Here's an example in which it was used in a selective soldering application. A customer was having poor hole fill on a bare copper bus bar, and it required 100% touch up on all joints after selective soldering. So obviously this increased costs and caused significant production delays. They asked AIM for help. We tried out our REL61 alloy with our FX16 flux, and they were able to get 100% hole fill with excellent aesthetics on all of their assemblies. They went from requiring touch-up on nearly all selectively soldered joints to virtually no touch-up required, and had 100% hole fill in this application. Here's an example where REL61 was used in a wave soldering application. The customer was experiencing excessive solder dross when they were using SAC307, so they wanted to try out REL61. And we're also comparing that with SN100C. So we tried this out. The results, X-ray inspection of the components processed with REL61 showed 100% vertical fill on all of the components. It provided better wetting and smoother joints than what they got with the SN100C. And dross was not specifically measured, but it appeared to dross less than the other alloys. So they had improved wetting, 100% hole fill, smoother joints, and reduced dross. As another example, it improved barrel fill and eliminated bridging compared to SN100C and a wave selective application. So they tried out our REL61. After optimizing everything, REL61 consistently achieved 100% barrel fill and eliminated bridging. And even with different parameter settings, REL61 performed well, which also indicated a nice wide process window. They were able to successfully transition from wave to a selective application. They eliminated all of the bridging problems, had 100% whole fill, and a nice wide process window. So now let's summarize what we've discussed with REL61. So it's important to note what REL61 is and what it is not. So REL61 is a cost-effective SAC305 alternative. So it will save money. It also outperforms SAC305 and many other low, no silver alloy options. So anyone who is looking for a cost-saving measure, who is using SAC305 and wants to save money without compromising performance, REL61 is a really great option in this situation. The other thing to note about REL61 is its versatility. So it is phosphorus free, so you can use it in wave and selective soldering applications without degrading the nozzle. It's available in bar, in wire, and in paste form, so you can use it across all types of production lines. It's also lead-free compatible, so it is compatible with most elements in lead-free environments, including SAC alloys, nickel finishes, and trace germanium. However, what it is not compatible with leaded alloys. So if you have a mixed environment where lead solder or components may be present, then that may be a case when you do not want to switch to REL61. It is also not considered a high reliability alloy. So that's sort of a different class of alloy. That's our REL22 offering. So REL61 does outperform SAC305 and similar alloys in many metrics. It doesn't quite meet the standards of a high reliability alloy like REL22. And this is just a review of a comparison of those mechanical properties. We had shown how REL61 compared to SAC305 in the beginning. We also have some comparisons with SN100C. Here we have a more significant difference in melting temperature, and some other differences across hardness and wetting time. And this is REL61 compared to SAC307. Again, we've had that slightly lower melting range, that improved hardness, and so on. And that brings us to the end of our presentation. I hope you learned something about our REL61 alloy. If you have any questions at all or want to consider this alloy in your applications, please visit our website, aimsolder.com, and contact us or reach out to our technical support people. Thank you very much.